Hello class, welcome to the third review for Unit Test 2, Matter and Energy. For this unit test, please make sure that you are familiar with the vocabulary words, you are familiar with the unit objectives, and you pay special attention to the bold, big ideas from the unit. Now let's begin with a discussion of the differences between solid, liquid, and gas. So sketching the particle diagram of a solid, notice how the particles are in a regular geometric pattern. That would be a key word that you're going to look for when examining the particles of a solid. Of a liquid, the particles are still very tightly packed, but they don't have a regular geometric pattern. And then we have gases finally. Their particles are very far spread apart and they're in constant motion. As you can see, I have completed the chart that describes the various states of matter. Solids particles are arranged in regular geometric patterns. They have definite shape and definite volume. That means that their volume is not dependent on the container in which they're placed. And they have extremely strong intermolecular forces. Those are the forces that are holding one molecule adjacent to the next. Liquids, on the other hand, because of their moderate intermolecular forces, they still have a definite volume. Means their volume does not change based on the container, but their shape is indefinite, or it takes the shape of a container. Lastly, gases have no intermolecular forces. Their lack of intermolecular forces mean they have a lack of shape and a lack of volume. Therefore, gases will completely fill any container in which they're placed. Looking at question 1, it asks, at 101.3 kilopascals of pressure and 298 Kelvin, which element could the diagram represent? So when we examine the diagram, we see that it's a regular geometric pattern. This diagram looks like a solid. So basically the question is asking which element is a solid at room temperature. To answer this question, we need to use reference table S. 202, 211. So now I've gathered all of this melting point and boiling point data from reference table S. It's time to apply it to a number line. Now, the number that we're going to be inserting in this case is 298. So, remember that if it falls to the left of the melting point and boiling point, it's a solid. To the right, in between the melting point and boiling point is a liquid. And to the right of melting point and boiling point is a gas. So the number 298 will fall here. So this means that radon is a gas. Now silver, 298, will fall over here. So silver is a solid, and then we have xenon, which is a gas, and krypton is a gas. So the only solid here is silver. So silver would be the best answer. So for this next part, we're asked to identify each of these things as elements, compounds, or mixtures. So in picture A here, we can see that the particle consists of two different atoms, represented through shading, that are bonded together. So this would be a compound. Now in picture B, we have that same compound, but then we have a different picture here because there's a different ratio of atoms bonded together. So since there's two different particles here, we are going to have a mixture. Now, in the next example, we have this duet of particles. Now, notice that these particles are the same atom. They're identical, so that's an element. And the next particle in the same portion C is right here, and that's a compound. So since we have an element and a compound, that's a mixture of an element and a compound. Now in this sample over here, sample 1, we have this duet here that again is an element. That's called a diatomic element because it is made of the same atom that's stuck together, and then we have this other element. So here we have a mixture of two different elements. Now, in sample C, we actually have the same thing in sample 1 meaning we have a mixture of two elements, but the elements are a little bit different here. So we have these open circles here. That is one element. They're not bonded to anything. And we have the closed circles. So again, here we have another mixture. And then lastly, you can see that we have this duet of atoms together, all one kind of atom. So here, what we actually have is we have an element. Finally, we're asked to classify these chemical symbols as elements, compounds, pure substances, and mixtures. And recall that an element or compound is a pure substance, and a mixture is not a pure substance. Now, if we look up at the diagram above, again, a pure substance, every particle is identical. So we can see here when we have an element or a compound, we have a pure substance. But when we have a mixture, the particles, circled in red and or blue, are different. So that's basically what we're going to use for this. So first we have sodium chloride. Now sodium chloride has two capital letters, signifying that it has two elements, sodium and chlorine. And this chemical formula is bonded together. So this is a compound, and all compounds are pure substances. Now next we have H2O. Now again, two capital letters, H hydrogen and O oxygen. So we have a compound which is a pure substance. Now in this example we have sodium chloride, but it's aqueous, meaning it's mixed with water. So that's going to be a mixture. Next we have mercury nitrate, and it is aqueous. So anything aqueous again is a mixture. Now, nitrogen gas. Nitrogen only has one capital letter, the capital N, so that is an element. Notice that the subscript was not important in this case. Magnesium, Mg, that is only one capital letter, so that is an element. And then H2SO4, which is sulfuric acid, here is actually going to be a compound because they have actually three capital letters, a hydrogen, a sulfur, and an oxygen. They're all bonded together. And remember that all compounds are pure substances. Now, here we're asked to look at changes and identify them as physical or chemical changing. So dissolving, when we dissolve salt into water, we still have salt and we still have water. We haven't actually chemically changed anything, so that would be a physical change. Melting of iron, I still have iron, it's just molten or melted, so that again is a physical change. Burning of wood, if I take a piece of wood and I burn it, I turn it to ash, its name changes because its chemistry changes, so that is a chemical change. And when a liquid forms a gas, when it evaporates or boils, we still have that substance. So when water boils, it forms water vapor, so that again is a physical change. The next portion here is referring to a phase change diagram or a heating or cooling curve. And it asks, as a phase change is occurring, so remember on this heating or cooling curve, we have some very important parts. We have a solid, we have a liquid, and we have a gas. And at all these points it's heating up because our Y value is temperature and our X value is time. So that means that we're having a phase change is occurring on any of the plateaus. So we have a solid turning into a liquid called melting at the first plateau, and a liquid turning to a gas or evaporating at the second plateau. But recall that on this graph, there's only one type of energy is changing at a time. So at all the sloped lines, we're going to have our temperature, which is the same thing as kinetic energy, is increasing, while our potential energy is constant. And at the plateaus, we have the kinetic energy is constant, while our potential energy is increasing. So to answer this question, our kinetic energy would be constant. Now, when we transfer energy, when ice cubes are placed into water at 45 degrees Celsius, that is a difference in temperature, which will result in a transfer of thermal or heat energy. So melting of ice and water is not a chemical change. So we're going to change some thermal energy And remember that heat only flows in the direction of hot to not. So that means that the warmer water will be giving its heat to the ice. So number 4 is the best choice here. Question number 4 asks us to examine reference table I and describe what occurs when sodium hydroxide pellets are placed into some water. So let's pull up reference table I. So here on reference table I, we're going to look for sodium hydroxide and dissolving in water. So we can see that that reaction is here, and some information on the reference table is given over here, this delta H value, and we see that this value is negative. Now when I read down here, it tells me that the minus sign indicates exothermic. So we know that this process is exothermic. Now the word exothermic, exits, means heat energy is exiting the particles. So let's kind of try and draw a diagram of what's actually occurring. So here I've drawn a beaker of water. The beaker is green. A beaker of water with sodium hydroxide inside. And recall that reference table I gave us this negative number, meaning that this salt has heat exited when it is placed or dissolved into water. So if I were to go and sketch heat in this diagram, I'd say the heat's exiting the sodium hydroxide. When the heat exits the sodium hydroxide, it exits to the surroundings, which here is water. So in this case, we would expect for the water temperature to increase, and the energy that was stored in the sodium hydroxide, the chemical energy, is converted to heat. So number 1 is the best choice. The next question asks us how much heat energy must be absorbed to completely melt 35 grams of water. So whenever we have these heat energy calculations, so here we have the word heat, we're going to have to look for some keywords. So in this point, we see the keyword melt, and we also see the key temperature 0 degrees Celsius. So notice that the temperature is not changing. When the temperature is not changing, we're going to have to refer to reference table T for a heat equation that does not have the change in temperature. So from reference table T, we can see that we're going to want one of these two equations, the Q equals M times H. Now the question is, which H do we have? And we have to choose between fusion and vaporization. So vaporization is making a vapor or boiling. So melting is synonymous with fusion. So we're going to use this equation. Q equals MHF. So now we want to look and see, what do we know the question? Well, in the question, I can see that I have my mass here. So this is my mass. I'm looking for heat, so I'm not sure of that. And now we have this one more variable, this H sub F. Remember, in all of these heat equations, there's always going to be one variable, and it's either the C or the H's that are actually going to be found on reference table B. Here you can see on reference table B, we're going to use the heat of fusion.
Just like Lucas for.
Right, the heat of fusion is 334.
Yeah.
So what we're going to do is we're going to take 35, our mass, times the heat of fusion, 334. When you put this in your calculator, it will give you a different number. But remember that all numbers on multiple choice questions are rounded to the correct number of significant digits. So the rounded number will be closest to this number 3. The last question asks us which form of energy is converted to thermal energy when propane burns. So then the question is, well, what kind of change occurs when something burns? And we know that's a chemical change. So that would be chemical energy is converted to heat energy.